Hello and welcome to the online workshop Introduction to Molecular Dynamics Simulations. This is Module 1. In this module, we'll take a very brief overview of molecular dynamics simulations. Before we start, a little bit about myself. My name is Siddharth Gautam. I did my PhD in physics from Bhabha Atomic Research Center in Mumbai, India. After that, I spent 3 years working at Donostia International Physics Center in San Sebastian, Spain. And since 2013, I've been working with the School of Earth Sciences, the Ohio State University, Columbus. And just to help you locate where this city Columbus is, in the map of United States, you can see different states. In particular, just south of the 5 Great Lakes, you have a state which is called Ohio, and Columbus is the capital of Ohio. So, in this module, we'll be talking about these topics in particular. We'll start with talking about what is a simulation in general, and then we'll talk about why we need simulations after all. We also need to talk about what is the need for molecular level information, and then we can talk about some experimental techniques that can provide this molecular level information and their limitations. After this, we'll then be able to talk about the need for molecular simulations, and after this discussion, we can then go and take a brief overview of molecular dynamics simulations. And finally, before closing, we need to distinguish between two different types of molecular dynamics simulations, that is ab initio and empirical MD simulations. In this workshop, we'll be focusing on empirical MD simulations. We'll see later. So, what is a simulation? Oxford Learner's Dictionary defines a simulation as a situation in which a particular set of conditions is created artificially in order to study or experience something that could exist in reality. These simulations can be real life simulations, or they can be simulations performed on computers. We'll see examples from both these cases. Talking about real life examples, we have seen children playing, and indeed when we were children we also played games like playing doctor. These games are in a way a simulation where children pretend to be doctors, or sometimes they pretend to be patients. Another example can be movies in which actors play different characters and they try to simulate different events in one's life, fictitious or real. Yet another example of a real life simulation is a crash test of automobiles. So, for example, automobiles conduct fake accidents with their motor vehicles with dummies sitting inside. The idea is to see how these dummies can get damaged in an accident, and a similar fate can be expected for the drivers and passengers. So, in all these real life simulation examples, there can be a lot of imagination and creativity. For example, in kids pretend plays, there is a lot of imagination and creativity. Whereas if you consider crash test, on the other hand, there is more accuracy with respect to laws of nature rather than creativity. Here are some examples of simulations done on computers. So, for example, one can simulate the collision of two galaxies. For example, Here you can see time frames from the simulation of collision of two galaxies. This work was published in Nature in 2005. You can see the two galaxies as two blobs. They are coming together, they collide, and after some time come they just merge into two different clouds, gas clouds. Another example can be a flight simulator. They can be games. For example, you can play a game of a fighter plane pilot, or sometimes these simulations are also used for training purposes. Training pilots can use flight simulation techniques. They can sit in a module which can move according to how the plane is moving. In general, this is a combination of real life and computational experiment. Another example can be a much lower length scale example of molecular simulation. So, for example, here you have a picture of liquid water. You can see different molecules of water with these red spheres representing oxygen, and I don't know if this is visible to you, but there are smaller whites or pinkish spheres which represent hydrogen atoms, and then you have connections between oxygen and hydrogen which show hydrogen bonds. We'll talk about that maybe later. The point is, computer simulations can span a very wide range of length and time scales, starting from galactic length and time scales, where the length scales are of the order of 10 to the power of 20 meters and time is of the order of 10 to the power of 16 seconds, which is a few billions of years, to human scale here, and all the way up to molecular scale, 10 to the power of minus 9 meters or nanometers, and 10 to the power of minus 12 seconds, which is also 1 picosecond, that is molecular scale. In fact, you can go even further, and people are making simulations of quark gluon plasma, where quarks are the ultimate subatomic particles that make up neutrons and protons, and gluons are the particles that bind them together. So simulations have been done even at that scale. So now if you have seen enough examples of simulations, both real and computational simulations, the question is, why do we need simulations after all? And the answer is, if you want to understand nature, there have been two traditional ways of understanding nature. First is, you do observations, you observe things, try to understand them, or do experiments, actively perform experiments to understand things. These experiments can be expensive. You need to put in a great amount of effort, money, and time in performing these experiments. They can be very difficult also, and sometimes they can even be dangerous. Another way has been the logical deduction. For example, you can start with basic laws of nature. For example, you can start with Newtonian equations of motion and work out solutions to your problems. You can find exact solutions by making use of logical deduction. But exact solutions are not always possible. There is, since the second half of the last century, there has been a great computational power made available, and this has made a third way possible, that of computer simulations or computer experiments. These are relatively cheaper. You just have to have a computing machine, you can have a laptop or a desktop. They are relatively easier to perform. You don't need to depend upon any other equipment, and there is no danger involved in these experiments. You can even simulate fires, you can simulate very high pressures, you can simulate anything that involves danger, and it won't cause any danger to you. So if you want to have simulations, we are in particular talking about molecular dynamics simulations. So then the question is, why do we need molecular level information? And the answer is, we all know that macroscopic properties are determined by molecular behavior. So for example, intermolecular distances and interactions determine the phases of matter. So for example, if the atoms are arranged in a very regular fashion and quite close to each other, your system is a solid. As the intermolecular distances increase and there is more freedom for these atoms to move away from each other, you get what looks like a liquid. And if this distance, interatomic distances, become very large and the velocities become very large, what you get is a gas. Another example is that of a pathogen attack. So for example, you have a picture, a schematic of a coronavirus here, and you can see that this virus has spikes on its body, which is made up of proteins. The way this virus attacks an animal cell is it docks with a receptor, and if you want to somehow make this virus ineffective, one way of doing that is to somehow block these spikes from docking with the receptor. But if you want to do that, you need to understand the molecular geometry, or in general geometry of the acceptor and the receptor, and all these things have to be understood at the molecular level. So you need to have a molecular level understanding in order to effectively find a solution to a pathogen attack. Yet another example is that of gas storage and separation using nanoporous materials. So for example, one of the major concerns we have at this moment all over the world is the rising levels of carbon dioxide in the atmosphere. The question is there a way we can somehow take it away from atmosphere and store it somewhere? And a promising candidate for this is a class of materials which have nanopores. That means these materials have pores of the order of a few nanometers. So for example, here you can see a picture of ZSM5, which is a silicon dioxide material. So you can see blue spheres here represent silicon and red spheres represent oxygen, and they are arranged in such a way that you have some porous space left, and some molecules can get trapped in these porous space. So for example, here we have an example of ethane molecule. There you can see some ethane molecules trapped here in this pore, and all these pores. Once these molecules are trapped into these pores, because of the strong interaction with the substrate, that is with the silicon and oxygen here, it is sometimes difficult for these molecules to escape, and this way you can store gases. Another example is that of hydrogen. So for example, we want to use hydrogen as a fuel, but then the problem right now with hydrogen is that of storage. Because hydrogen is a light gas, if you want to store a good amount of hydrogen, you need a very large volume. But if you can store hydrogen in such nanoporous materials, you can compress a great amount of hydrogen in a very small space. Here is another example of a porous material, which is NaY zeolite, and you can see some butadiene molecules trapped into these pores. This is yet another example of a porous material, which is actually a metal organic framework, where you have a metal and some organic molecules coming together, forming a very regular pattern, giving rise to pores. So if you want to have molecular level information, the question is, should you apply quantum mechanics or classical mechanics to understand matter at that level? One way of deciding whether to apply quantum or classical mechanics is to find out the thermal de Broglie wavelength of material in question. The thermal de Broglie wavelength of a material or of an object can be calculated using this expression, where h is Planck's constant, m is mass of the object, kb is Boltzmann constant, capital T is the temperature in Kelvin scale. So at 300 Kelvin, you can work out these constants, and if you express mass in the units of atomic mass scale, then this expression comes down to lambda equal to 4.6 upon square root of mu in angstrom units. And you can very well see that if mu is greater than 4, then this wavelength is always less than 2.5 angstrom. Now, just to remind you, mu is greater than 4 for most elements except for hydrogen and helium. So this means for most elements, even for atoms, it is okay to use classical mechanics as long as you are interested in distances larger than 2.5 angstrom. So this means for most practical purposes, for most molecules, you can study their behavior using classical mechanics. Some experimental techniques that provide molecular level information. You can do some scattering and diffraction of particles. You can use X-rays, you can use neutrons, protons, light. Interaction of matter with light can be used to study its properties. Also, interaction of matter with magnetic or electric fields can also be used. So I think some participants in this workshop are familiar with small angle X-ray scattering, and at least one participant is familiar with dielectric relaxation spectroscopy. So these are some experiments that can provide molecular level information. But all these experiments have their own limitations. One is, of course, they are very expensive. So, for example, if you are talking about scattering of particles, scattering of neutrons, to be able to get a good amount of neutrons, you need to have very high flux reactors or synchrotron or spallation sources, Similarly, for X-rays, you need synchrotron sources. These are very large, very expensive facilities. Even for electric fields, um, you can you can imagine electric fields might not be that expensive, but then we need to understand that if you want to have molecular level information, you need to have uh, ability to measure these electric or magnetic fields with a very high sensitivity. So that makes these experiments very expensive. Also, all these experiments provide incomplete information. So, for example, if you are using X-rays to study material, you won't be able to see hydrogen atoms in presence of any other heavier element. So, if you have water, for example, mostly you'll see oxygen atoms and hydrogen atoms will be invisible. On the other hand, for example, in neutrons, if you're using neutrons, only hydrogens will be visible, oxygen won't be visible. So each technique has its own limitations and they provide incomplete information. And finally, some of these experiments can be hazardous to humans. For example, all experiments having to do with radiation, be it synchrotron radiation, light, X-rays, neutron scattering, they can all be dangerous to humans. One way of avoiding that is, of course, to do molecular dynamics simulations. What you do in molecular dynamics simulations is, given a system of molecules in thermal equilibrium, the idea is to simulate the motion of each participating atom. So, for example, here you have some propane molecules. You need to simulate the motion of each participating atom here. This would result in a molecular movie over time. So, for example, here at one particular point of time, say starting t equal to 0, your system might look like this. At t equal to 1, the system might look like this. At t equal to 2, the system might once again look like this or some other configuration. And this way, you'll have a molecular movie over time. Or in other words, position of each atom at different times is obtained. This is called trajectory, atomic trajectory or molecular trajectory. This molecular movie can then be studied and average quantities calculated from the trajectories to understand the behavior of the system. And how exactly it is done? So what we do is, to start with, we make an atomic model of the system to be studied. So just to give you the same example of propane, we take some propane molecules as starting configuration. This constitutes what is called a simulation box or simulation cell. So for example, this can be considered as a simulation cell. Once you have this model, you write down the equation of motion for all the atoms in the sample. That is, you write down the Newtonian equation of motion. So for example, for conservative systems, the equation of motion is mass times acceleration is negative gradient of some interaction energy. And then you solve the equation of motion numerically. So the input that you use in your computer is position of all atoms, that is r at time t equal to 0. This is what you have at r t equal to 0. And you also need the form of this potential, which is also called force field. You also need the initial velocities, v at time t equal to 0. These can be determined by the temperature of the system. And when you solve the equation of motion numerically, as an output, what you get is position of all atoms for all times. That is, you get trajectories. Or r as a function of t, where t is any arbitrary value, and also v as a function of t. Once you get these trajectories, then you can calculate various thermodynamic and structural properties of interest from these trajectories, because ultimately all the thermodynamic quantities and structural properties can be expressed in terms of RT and VT. Finally, as I alluded to earlier, we need to distinguish between two different types of simulation, molecular dynamic simulations, that is ab initio versus empirical. So we agree that motion of atoms and molecules can be treated classically, but their interaction is governed by the electronic structure that can be treated accurately only in quantum mechanical formalism. So this means UI, that is force field, is to be estimated from quantum mechanical calculations. When this is done, the simulation involves both quantum mechanical and classical mechanics. So for example, force fields are described by quantum mechanics, and equation of motion calculations are done using classical mechanics. This approach is called ab initio molecular dynamics, where ab initio means from the beginning or without making any assumptions. Another cheaper alternative is to approximate the force field by a classical model, that is obtained empirically by comparison and fitting with experimentally measured data. This is empirical molecular dynamics. In this workshop, we shall focus exclusively on the empirical force field based molecular dynamic simulations of systems under equilibrium. Before we close, a few things about the rest of this workshop. Each module will have assignments. So after every module, we shall prescribe some assignments in different categories. The categories are, first of all, reading assignments. These will comprise of papers or web pages or parts of papers or web pages which will help in the understanding of the next module. Then there will be concept assignments. These will comprise of finding about and trying to understand concepts from standard textbooks and or web pages. So we'll just give you a concept and then you need to find it out on your own using internet or your standard textbooks or whatever. Third type is pondering assignments, and these are quite interesting and I think quite important too. These will comprise of questions that the participants are expected to think about and discuss. As in this concepts assignments, number 2, these assignments will also make some concepts involved in the current or the next module clearer. And finally, we'll have plotting assignments. These will help the participants familiarize themselves with using the allied softwares, Vesta and GNU Plot, and at the same time help them understand some key concepts. And finally, I should mention that these assignments are meant to facilitate understanding and not to serve as tests. So the participants are expected to approach them with a playful attitude rather than taking them as a task to be completed. So this brings us to the assignments from module 1. I won't read these assignments because that would be very boring. You can read them yourself. I'll just describe them very briefly. So the reading assignment involves a paper which has a DOI given here. For those who are unaware of what DOI means, it means digital object identifier. So this is a sort of identity of any paper or a movie or any documentation on the internet. This has a unique number. You can try to find this paper. This is an open access paper and you just need to read page number 8 of this paper. No need to read the whole paper. You need to find out about different statistical ensembles: canonical, microcanonical, grand canonical, and then pondering assignment. This is quite an important one. Here we need you to think about if MD simulations can be used in a given situation. So just to give you an idea about where MD simulations can be applied, where they cannot be applied. Here's a plotting assignment. You need to plot this function. This is a potential energy function. You can do this plotting using GNU plot, which is I believe you must have installed it just as you install DL Poly or and Vesta. For beginners who have had no previous exposure to GNU plot, they can get quick help with GNU plot. That is how to plot, how to start GNU plot by looking at this web page. This is basically a document, GNU plot for beginners. And we try to use GNU plot because this is an open access, open freeware. But if you are more comfortable with any other different plotting software, and if you want to use that, you are welcome to do that. Here is some more further reading. We do not expect you to read all this material, but this serves as a reference just in case sometime later you want to refer to something related to molecular dynamic simulations. You can refer to these resources. So first two of these are standard textbooks. They are very good textbooks about molecular dynamic simulations. This is a paper which talks about molecular dynamics simulations and applications specifically for bioinformation and biochemistry. This is yet another review paper on molecular dynamics and applications focusing on nanotechnology. Sorry about that. And that's it. This is end of module 1. Thank you.